Okay, this video is to help you get started with our lab. We're going to study refraction from air to glass and from air to water, and then we're also going to look at what's called the total internal reflection at the critical angle. Okay, so you'll open up that hyperlink and you'll see this bending light. That's the refraction, the bending of light. And you click on the intro and you'll see this is what comes up. So the first thing you need to do is make sure this is on ray. That means you can turn on the little red laser there. We're going to assume that wavelength is 650 nanometers. It turns out that the human eye is can respond to various wavelengths or frequencies of light, and your eye is sensitive to wavelengths between about 400 nanometers and 700 nanometers. 400 nanometers is in the violet and 700 nanometers is in deep red. And so this color of red looks to me to be about 650 nanometers. That is a typical aluminum, gallium, arsenic laser diode, one of the first ones that was ever built. Anyway, I'm going to take this protractor. This is important. You want to line up your protractor well. And how you do that is notice how I see that. Okay, this is going to be interface 1 up here. We're going to use, in this first lab, this is going to be air. And there's something you need to understand called the refractive index, the letter N. Now, the refractive index of air, see, is 1. See, water is 1.33, 1.34. Actually, water, if you put it right there on water, it should be 1.33. I can't forget it. What the heck? There we go. That's water, and then glass is 1.5. Okay, that I'm controlling the refractive index up here. This one controls the refractive index down here. So let me name everything. This is the interface right along here between the two medium, right? We got air up here, and right now we have water down here. I'm going to make this glass. Okay, so that's glass with an index of refraction of 1.5. So the bigger this number, the slower light travels. Okay, you'll learn about that later. Now, if I put this protractor here, I would do glass first in the lab because it bends more and it's easier to do. So I'm going to put this protractor up here, and notice how I got to get that line right on the dotted line there. See how 0 is on the dotted line right there and there, and then you want it as perfect as you can get it, and you'll know you're good if you do the following. Let's put this, okay, notice that 0 degrees, there's no bending, and you can look at the equation for refraction and see that's the case. And as I change the angle of incidence, now the angle of incidence is measured between the normal to the interface. Once again, this is the interface, and this is normal or perpendicular to the interface. See that dotted line? So if I kick the laser on and I rotate it, notice that I can go from 0 degrees all the way to 90. And notice that, see how the light bends? When it goes into the medium, it bends toward the normal. See that? Look, here's this exaggeration here. There we go. Over here, way over here, about 65 degrees, we can see that this light, when it hits the interface, it gets bent toward the normal. So you need to understand that. Now one thing that's pretty obvious, like if you throw a ball at the floor, it'll rebound at the same angle that it hits the floor. Notice that if I come over to about, okay, there's 30. If I come over to 35, 40, 45 degrees, why that one? Well, that's halfway between 0 and 90. Okay, so if I put that right at 45, I should have the reflected ray at 45. See that? And that means everything's lined up pretty well. Okay, now, one thing that's interesting, notice how light this is. What that depicts is not as many photons or the intensity of the light, not as much gets reflected as gets transmitted. And that's a subject that's very complicated. It's called matching Fresnel coefficients. You have to use Maxwell's equations. That's way beyond the scope of anything we're going to study, but it's really interesting. And you could actually measure the intensity. You can see that, for instance, there's 100% intensity. See how 90% of it's getting refracted into this medium? And only about 10% is getting reflected. See that? Anyway, but we don't need that. Okay, now, so what you're going to do is you're going to change this angle. You're going to go in increments of 15 degrees. You're going to go to 10, 15. See that? 15 is going to be your first measurement. So you can see it's lined well. There's 15 reflected, 15 incident, and then you got to estimate. It looks to be about 10 degrees is the refracted angle. See that? So you measure your angle from the normal. That's the incident angle from here to here. Here's the reflected angle from here to here. See, those are the same, right? The incident angle, that's the incident ray, is the same as the reflected angle. See, incident angle, theta sub I, is the same as reflected angle, theta sub r. And then it gets refracted or transmitted into the glass, and this angle right here from this dotted line to the laser beam is your, I call it theta T, theta transmitted. Okay, see that? So you're just going to go at 15 and measure it, and then you're going to go to 30. 30, see how it's lined up still? 30 degrees here, 30, and then that's about what? Just a little shy of 20. I'll let you estimate. Whoops, I just messed up the protractor, didn't I? Turn it. There we go, it looks good. Okay, then we go to 45, so there's 40, here's 45. That's half a 90, right? 45, you can see it's bending toward the normal. If it were going straight, it would be like this, right? Anyway, there we go, and then I keep on going. What's the next angle? 45 plus 15 is 60. You can see it's still looking good. It's still, everything's aligned properly. And then on 75 degrees, which would be right there. So those are the measurements that you need to take. Now watch what happens when I change to water. Water has a less index, so this won't be bent as much. So glass has an index of refraction of 1.5. If I go to water, see how it doesn't bend as much? And in fact, if I go to air, it doesn't bend at all. Watch. Well, I can't. It won't let me. There we go. See that? No bending at all, air to air. Why would it bend? But as we change medium, we can see it bends toward the normal. When you go from a lower index to a higher index, by the way, the index of refraction of air is about 1. And generally, the index of refraction of clean distilled water is about 1.33. So make sure you put it there. And then now there's all kinds of glass. But borosilicate crown glass is about 1.52. We're just going to use 1.5 for glass. There's really interesting properties of glass. There are people that their whole career is studying the optical properties of glass. Of course, it's very important. We use it for many, many things. Okay, now, so you're going to repeat this experiment with air to glass and air to water. Okay, now, let's see, how many minutes is that? It's 6 minutes. I'm going to keep going. After you do the two labs involving, get the measurements at 15-degree increments for air to glass and air to water, then what I want you to do is change this from water to air. Now watch what, now by the way, let me show you something. Light, because of conservation of energy, light is time reversal symmetry, So if we were coming in this way, this is what would happen. See that? It would bend away from the normal and of course the reflected ray would be over here. But anyway, see how that refracted ray, if you could reverse this. You're coming in from glass to air and then it bends away from the normal. So basically watch. I'm going to change this to glass. I better make this angle less. It might get, okay, there we go. And I'm going to make this air. Now see how it bends away from the normal? Now here's what you're going to do. You're not going to do Snell's law with this. What you're going to do is you're going to find the critical angle. Watch this. This can only happen, this phenomena, which explains why light can be trapped in a fiber optic cable. And there's a lot of things, turning prisms. There's all kinds of applications, binoculars, poro prisms and binoculars that use total internal reflection. It saves all the photons and reflects them. But watch this. So notice this. I'm going from glass to air. Now notice how the reflected beam is still weak. Watch this. Only when you do this, see how it's going to, watch what happens when it goes to 90. See how this beam's getting stronger? We're getting more and more reflected. And then all of a sudden, boom. No more, right there is the critical angle. So that critical angle from glass to air is about 30, 40, I don't know, let's see, that's, 40, about 42, 43 degrees. So you can read about that and study those YouTube videos, and you can calculate the refractive index of glass up here from this physics. So I'll let you figure that out. Now what happens when I go to water? I'm going to need a bigger, from water to air, I'm going to need a bigger angle. Watch, see? It comes back. So I put it on 1.33, and then I need to make the angle bigger, see? But we do have a critical, this is the critical angle, see? When the transmitted ray reaches 90, watch how bright this gets right when I hit 90. When this ray goes to 90, that's the critical angle. Boom, right there. Boom, no more transmission. The light is trapped up here. So this has lots of applications. So that's what you're gonna do for experiment. I hope that helps. And I'm gonna also give you a little tutorial on graphing this time. I left you hanging last time with the graph, and I'll explain that later. But anyway, I've been really slammed with a lot of stuff, and hopefully this will be an easy lab. It's pretty involved. You need to get started, but you're gonna learn optics well because this is pretty simple. Okay, have a good day.